Okay, so let me say a couple words about this homework's a little bit longer than the other ones, but notice the due date. It's not due until a week from Friday, it's due the 20th. And there's more problems, but some of them are not bad. So the first one we hit on this theme of the divisible group, abelian group. Number A, show that any, if you have a divisible group, show that any homomorphic image of a divisible group is divisible. Number B, show that if you have a family of abelian groups, oh, I didn't even write it. This should be, I'll try to remember to correct this. This should be a family of divisible abelian groups. Otherwise, this is poppycock. Yes, each one of these DIs are divisible. Then the direct sum is divisible. And show that if A is any abelian group, then A can be realized as a subgroup of a divisible abelian group. So any group can be put in, any abelian group can be put inside a divisible abelian group. Number 2, show that the following conditions on the R module sequences are equivalent. Number A, this sequence is split exact. You're going to need to split this. And this Hom sequence is split exact. I haven't talked to you about what Hom is. We're going to get to that. But I'm going to give you some theorems that's going to do most of the heavy lifting. I think you can quote a theorem that I'm going to give you today or tomorrow that will do most of this work for you, which is good. Number 3, show that the following condition. Yeah, I assume that, you know, 1 implies 2 and 2 implies 3. Kind of, you don't have to do it that way. I put these as 5 points apiece. Consider this. I don't care how you do it. Show that these conditions are equivalent. I don't care if you do C implies B, B implies A. I don't care how you do it. You know, you can do A if and only if B, if and only if C, but why do the extra work? Anyway, so show the following conditions are equivalent. I is injective. If tornado from A to B is 1 to 1, then the induced map on Hom is onto. This is kind of weird, right? This goes in this direction and is 1 to 1. This bad boy goes in the other direction and is onto, right? And I put this on. This isn't a terribly hard problem once you get to it, but it is interesting. And if this is a short exact sequence, then the reverse is short exact sequence. And again, I'm going to give you a theorem that does most of this for you. Number 4, this is an important thing that I need to bring to your attention. It's a moral imperative that I ask this call. Suppose you have a commutative ring with identity. Show every R module is free if and only if R is a field. Now, you already know that if R is a field, then all R modules are free. The interesting part is the other direction. So think about that. The last 2 problems, 5 and 6, are designed to get you warmed up when we do modules over a PID and the canonical forms. So this is a blast from the past with some linear algebra. Some of these will be pretty quick for you. You can use any facts that you know from linear algebra. Recall that if A and B are similar and N by N are similar N by N matrices. What did I do there? Anyway, I'll kind of clean that up a little bit. I recall if A and B are similar, if there exists a non-singular N by N matrix, say P, such that B is P inverse AP. Show that if A and B are similar, then the determinants are the same. Show if lambda V is an eigenvalue eigenvector pair for the matrix A, then lambda is also an eigenvalue for B, and find the eigenvector that makes this work. And those 2 problems I think should probably be routine once I clean up the language here. I don't know what's going on with me. And number 6, show that the N by N matrix A is similar to a diagonal matrix if and only if A has N linearly independent eigenvectors, right? And this is, of course, these matrices are over field. Okay, any questions on that? So you've got a couple of weeks to do that, but you know, come let me know if there's any difficulties. And here we go. Okay, so the last thing we talked about was this. The last thing we talked about were these kind of dual theorems. Projective, number one, P is projective as per my diagram definition. Two, every short exact sequence of the form 0, A, B, P, 0 splits. And number three, there exists R module K such that P sum K is free. So it's the summand of a free module. And we had the dual notion of injective, the analog theorem, which I gave you in your homework. Number one, I is injective. Two, every short exact sequence, this time leading with the I, splits. And finally, if I is contained in B, then B is I direct sum K for some K. So it's a summand of any module, which is it's a direct summand of any module, which is a submodule. And one of the things that I gave you on your homework to kind of help you out that I said you could use without proof was that you can assume that any R module can be put inside an injective R module. This is a fact that we'll talk about a little bit later. And I don't know about you all, but when I did 3 implies 1, this is the way I went on that, using it there. Let me prove the projective version of this theorem. Proof. 1 implies 2. So we have the P as projective, and we want to show every short exact sequence splits. Let 0, A, let me bring that down. Well, A, B, 0, be our short exact sequence. Well, let's just kind of blow up this part here. I'm going to call this G, part that goes from B to P. So let's put that under the magnifying glass. Now we have G here. And now I'm going to do something that's really, really cheap. I can certainly augment this diagram this way by taking P to be the same module here and just this being the identity function. Because of the fact that P is projective, there exists H from P to B such that when I do H and then I do G, this is the identity on P. So in other words, I have splitting. So H is our splitting. And so that's the cool thing about this that theorem that follows is equivalent that we did with the split exact sequence. I only need to give that this splits and then automatically the other splits, which is kind of cool. 2 implies 3. Well, let's see here. So now we know that every short exact sequence with P at the tail end splits. We want to show there exists an R module K such that P sum K is free. Any ideas on how to do this? Okay, that's kind of the starting thing. I don't know much, but I know, P is homomorphic image. A free module. That's a big theorem that we proved, actually, right at the beginning of last session, that every module was the homomorphic image of a free module. So there is some F, P, and this is on to, we'll call this B. And I can expand this to a short exact sequence this way, right? F is on to P, it's got some kernel, I'll embed the kernel into F, and now this is a short exact sequence, right? Now, my hypothesis in 2 is every short exact sequence with P at the tail end splits. Therefore, signal splits. It must be the case that F is isomorphic to, in fact, explicitly, here K is the kernel of that homomorphism. Are you okay with that? In this one, the last one I think is the hardest one in a certain sense. But it's not terrible. Okay, so 3 implies 1. So we know that P has the property that there's an R module K such that P sum K is free. I want to show that P is projected. Right? So let's set up the diagram. So we have B, C, and I'll call this G and F. Now, I want to be able to project. That is, I find some function that goes from P to B that makes the diagram commute, right? But of course, all I know right now is that P is the summand of some free module. So it's free. Actually, so I know I've got this. And I know I've got this here. This is an inclusion. And this will be, I'll call this projection. Here, I'm going to define iota of x to be x comma 0 and projection of x comma y to be x. So projection just projects from the first factor and inclusion just includes into x comma 0, right? Now, let me point out that P is free, hence projected. We actually proved, I think, last time that any free module is projected. Y'all remember that?
Is it P plus K that's free?
That is correct. That is correct. She's right. So I've got to go from the top of the diagram. So that is to say, here's the situation here. Pi F goes from here to here. So there has to be I'll call this H, such that H then G is the same thing as coming right down the tree, which is, I guess, pi F. This is what I am given when I observe that P sum K, the free is projected, right? Let me also, what do we want to do here? So here's what I want to do. This at least gives me a way to take a stab at what the map from P is. So how am I going to get from P to V? I'm going to go inclusion and then H. I'm going to call this H prime, where H prime is do inclusion and then do H. And I'm going to make a final observation here. The final observation I want to make is when I do I guess, iota pi, this is the identity on P. Because if I start with X and P, then I go to X comma 0, then I project back to X. So that composition should give me the identity, right? Now let's look at H prime G. Well, H prime is H iota.
Dr. Gordon,
Yes.
shouldn't that be a pi iota gives you the identity of E?
Did I do it wrong again? We'll see. I do iota.
So it should
I'm sorry.
be,
What?
shouldn't it be, that's the identity of P sum K? If you do pi, then iota, right?
No, I did iota first, right? So you start.
Oh, right,
Right.
Yeah, that makes sense. Yes, sorry.
So, let's look at, I want to look at H prime G. And let's see, what do I need? I need HG is fine. H prime G is equal to iota HG. Or, I'm sorry. There we go. I think that one. H prime is. There, right. My H prime projection here should be do iota first, then do H. That's correct. So this should be H iota G. And
It should be G H prime.
oh, thank you. Yeah. That's what I did wrong. So let's try it again. I do H prime first, don't I? And then G. So when I do H prime G, this is G H iota. There we go, much better. And the GH is equal to F pi. But as we observe, pi I is the identity of P, which is F. So there we go. So P is projected. So there's the equivalences of those conditions.
Dr. Gordon? Since every what's the called? every R module is gonna be the homomorphic image of a pre-module.
Mhm.
What specifically is unique to P being projected? Like, what is unique about P here? Is it just that it's the direct sum of the free module?
Yes.
Okay,
That's exactly right. It allows you to put this up in here, and that of course we've shown is projected. Being, being free is incredibly strong condition.
Sure.
And being projective is, in a certain sense, nearly as strong,
okay.
right? I mean, it's not quite as strong, in general, but it's, like I said, in a certain sense, nearly as strong. So I've got some more dual theorems, which I'll kind of scratch through the proofs a little bit. It's corollary 12, 6, and 8. Suppose I have a family of R modules. R modules. Then the direct sum of these R modules is projective if and only if each one of them is projective. There is a dual one as well. J, a family of R modules. Anybody want to take a, just for fun, anybody want to take a stab at what I'm going to say next? You can tell with me. So I'm probably going to be injective because that's the letter injective starts with, right? The family, each IJ is injective if and only if the, wasn't each individual one? Each individual one is injective if and only if what?
The product.
Correct product. That's kind of cool here. It's kind of a dual result. Let me prove the projective result and see if you can kind of fashion your way through the injective one. Okay, let's suppose that so I want to pick one of these P alphas, right, out of this huge mess of projective modules. Since this is projective, there exists K such that K direct sum, INI, PI is free. And I'm playing a little fast and loose with you, but it's probably fairly obvious. But notice that K direct sum, PI, I in I not equal to alpha, direct sum P alpha is free. So in other words, all I did is I jerked the P alpha out of it. So one of these i's is alpha. So I jerked it out here, right? And so now this thing right here plays the role of the K. This thing, direct sum, this is free. So P alpha is projective. Cool. And the other way is also not too bad. And I'll tell you what, I'll play fast and loose with it's over. For the other direction, and if PI is projective, for all I, then for all I, there exists KI and FI such that FI is isomorphic to PI direct sum KI and FI is free. So this just takes into account that all the little PIs work. And if you look here, you take the direct sum of PI, direct sum KI. This is isomorphic to the direct sum of PI direct sum KI. And this is isomorphic to direct sum FI, which is free. Because each one of these FIs is a direct sum of some number of copies of R. So you have this perhaps very large orgy of sums of copies of R, but it's okay. These are all sums of copies of R. So this is still free. Now, what I played fast, anybody want to criticize me? Here's your big chance. I did play a little fast and loose on a couple of things. And one of them is that I can rearrange this way, right? See if you can prove that the direct sum works this way. It's not difficult, but it is a detail that I did gloss over. Any questions? Okay. So I'm going to give you another corollary, and then I'm going to give you my promised theorem about injectives, which I'm not going to really prove all the way through, but I'm going to kick you down the road. I'm going to show you where it comes from. Then start talking a little bit about Hong. So let me give you a corollary. This is more of a corollary to an earlier observation. Corollary to 12.610. Every R module is the homomorphic image of a projective. Here's my proof of this. Free implies projective, right? And since every R module is a homomorphic image of a free module, it is by its very nature a homomorphic image of a projective R module. Why do I make this observation? Because when you do homological algebra, for example, often what you want to do is get a more general projective resolution. So you start with a module. it's the homomorphic image. So you do this way, you start with some module. It's the homomorphic image of a projective module. Right? If this is an isomorphism, you're good to go. Or if this, yeah, it's a homomorphic image. So this is onto. If this is an isomorphism, you're done. If not, there's a kernel of this, and the kernel of this is the homomorphic image of another projective module. And the kernel of this is a homomorphic image of another, and so forth and so on. So you build these resolutions, and you can use this to do some interesting algebraic things. You can use it to peel back some layers in topology, for example. And theorem 12.6.11. Every R module, M, can be embedded in the injective particle. Every R module, M, I don't make you do kind of a full 9 on this one in your homework. One of the homework problems that I've given you that's due in a couple of weeks is show any divisible group can be embedded in a divisible, I'm sorry, any abelian group can be embedded in a divisible abelian group, right? And that's the analog, this theorem, in the case that R is the integer, right? Let me tell you how you might go about this. M as an abelian group can be embedded in a divisible column T. And that's what one of your homework problems will get for you. So you'll get that part down the path of the road. Now embed as an R module in the injective R module. On Z R. These are, well, remember what this notation means. These are the homomorphisms from R to D that are Z module homomorphisms. So these are an abelian group homomorphism. This can be construed as an R module. Think about how you might do that. And you could then this actually you can embed M in this, and you can show that this is an injective R module. Okay, we are going to now. Well, first, any questions for you? Right, the injective and injective stuff. I'm going to get under the hood of this thing called HOM, and this could be a pretty mess. Let's see if I get my maps all in order. The idea behind HOM is, well, so call HOM AB, or if I need the emphasis here, AB is the set of R modular homomorphisms. F, make it B. So you might have two modules, two R modules A and B. You might look at the set of all their homomorphisms. Now, this is an abelian group under pointwise addition. So for example, how many homomorphisms are there from Z2 to Z2? Well, I haven't given you a lot of choices, right? I mean, you got two elements of Z2, 0 bar and 1 bar, right? 0 bar goes to 0 bar no matter what, because this is a homomorphism. So the big question is where do you send the generator 1? You got two places to go. It either goes to 1 or to 0. So you've either got the 0 homomorphism or you've got the identity homomorphism. And so this actually is an abelian group, is isomorphic to C2. How about this one?
This is just a zero.
It's called. The generator here in C3 has to go somewhere over here, right? But the order of the generator in Z3 is 3. So it has to go to something over in Z5 whose order divides 3. And the only divisors of 3 are 1 and 3. And that's a group of order 5. So you have to send the generator to 0, which forces all homomorphisms to be 0 homomorphism. Here, N is a natural number. What's this one? This one is also 0. Because the generator here has finite order. Nothing here has finite order except for 0, so it's got to go to 0. How about this one? This one is.
Oh, Z.
Is ZN. This is kind of, one way to see this is Z is a free Z module. And so the homomorphisms are just determined by where you send the generator here 1, and it can go to any of the things over here. And it's fairly easy to, I'm sorry, the CN, it's fairly easy to show that in fact what you get is CN. So let me look kind of at a more general situation here. We're going to, so suppose we have R module homomorphisms. We're going to actually do something a little bit more specific than the generality I'm going to give you here, but this is just kind of taking a look at the big picture. Suppose we have R module homomorphisms. stick my notation here, we'll say gamma that goes from C to A. We'll say, tornado goes from B to D. This can help us build a map. Call it Ada. From Homar AB to Homar CD. My input is F. Okay, so let me see if I can figure out what this is supposed to be. Okay, so I've got this input here. It's a homomorphism from A to B. So but then I have this other crap. I'm trying to get a homomorphism. I'm trying to use F and maybe these tools up here to get a homomorphism from C to D. And here's what I know. I know I've got gamma here. And I've got whatever I call it, yeah, tornado here. Right? So my input is my lowly little homomorphism from A to B. I need an output that gives me a homomorphism from C to D. So I guess I could augment this F by, I guess, do gamma first, then F tornado. Everybody okay? Notice it's pretty easy to see that this is an abelian group homomorphism, right? Because under the pointwise addition. So remember, in Hom as an abelian group, it's just pointwise addition. We refer to this as the homomorphism induced by tornado and gamma. And it is a homomorphism because if you do F plus G, you compose F plus G pointwise and you get exactly what you're supposed to get. We will often concentrate on the following special cases. So here are the special cases that we will give most of our focus to. The case first where B equals D and 1B. Then this map becomes and this is sometimes called the map induced by gamma. So we have home R AB to home R CB. This is called gamma bar, or gamma bar of F is F. Notice, in a certain sense, this reversed the order of what gamma, right? Because originally gamma goes from C to A, right? And when we do this, when we start from a homomorphism from A to B and we go from C to B, it reverses the order. Right, gamma bar F, F gamma, so the original gamma goes here, induced gamma goes sort of in the opposite direction. This is called contravariant. You could do the same thing by letting A equal C. So my other special case will be A equals C. And in this case, gamma is the identity on A. So then what we have here, we have F goes to tornado F. So we now have R from the home R AB to home R. And in this case, what happens is you have equals notice now we're letting the second coordinate, if you will, vary, and in this case, it goes in the right order, right? The original tornado went from B to D, and this thing makes the homes go this way in this composition. This is called covariant hom, right? So when you freeze the first variable and go along, then the maps go in the way you think. When you freeze the second variable, they reverse order, which is kind of cool, right? And so I think we will pick, this is a good place to quit. We'll pick it up next time and talk about what this does to exact sequences and so forth. So, any questions? Questions? All right. We will see you folks then on